Welcome to EE252 Electronic Devices and Circuits. Today we are going to talk about BJT H parameters obtained from transistor characteristics. Okay, so if you can remember, the output characteristics of a transistor BJT transistor it's basically a functional relationship between the output current IC and output voltage VCE with input current as the parameter. Okay, input current IB as the parameter. So that's why you had multiple curves for different IB values. So what we are going to talk about is how we can use this output characteristics to obtain certain H parameters and also the input characteristic. The input characteristics were basically a functional relationship between input voltage, that is VBE, and the input current IB with output voltage as the parameter, that is VCE as the parameter. And actually we did not go through this during the formal discussion about input characteristics. We said the input characteristics were almost similar to a diode's input characteristics, but we are going to talk about that a little bit more today, and we are going to say that it's a little bit more than just the diode characteristics, and that it depends not just on IB alone, but also on the VCE, whereas for a diode you don't have a VCE, right? So therefore this is going to be a little bit different, but you will see that the difference that is introduced due to this additional variability is very small, so therefore often we can neglect it. Okay, so this VBE versus IB or IB versus VBE input characteristic also gives us some, we can use this characteristic also to obtain some H parameter values. Okay, right. So let's get started here. H parameters can be predicted by looking at the input and output characteristics. That is what we are going to see. So first let's have a look at the output characteristics, which is what we are more familiar with. Output characteristics. The output characteristic is a functional relationship between the output current IC and the output voltage VCE with input current IB as the parameter. So if we draw the output characteristic, maybe you may remember this. So what you have, IC versus VCE, and you had several curves. I'm gonna exaggerate the features a little bit though, so that we can actually see what we can demonstrate what we are actually going to see. Okay, so I'm gonna have them like this, a little bit of curvature as well as not perfectly parallel. Okay, so let me take this as my different IBs. So let me take this as my IB equals IBQ curve, and let's say can choose this point as my Q point, ICQ and VCQ, I like that. This is my output characteristics. So earlier in the previous lecture we derived the fact that using Taylor series expansion of VBE and IC, the fact that HFE can be written as DABA IC over DABA IB at VCE equals VCEQ, right? So what is this? This is actually, so VCE equals VCEQ means that you are on this line. Okay, you are on this line because this is the VCEQ. That's this condition. On this double IC, which means a variation in IC, right? So let me say delta IC over delta IB. So this is approximately equal to, let me take this as IB, simple IB equals IB2, and this is IB equals IB1. Corresponding to that, when VC is equal to VCEQ, this, let me say IC1, this IC2. Okay, so what this is IC2 minus IC1 divided by IB2 minus IB1. So these are what I have. So what is this? So ratio between two changes of currents. This is a current gain. If we had perfectly parallel lines which are horizontal, right? If they are horizontal, then their gaps between each was the same. Whether you have VCE equals this VCEQ or some other VCEQ, it doesn't matter. Your current gain would have been the same. But unfortunately, practically it is not the case. If you change VCEQ, say for example here, then your differences may not be the same. Okay, they may not be the same. So therefore, it is possible that they change with the Q point. Okay, right, that's one thing. The second relationship that we obtained was for the another relationship, not the second one, HOE. We obtained this to be double IC over double VCE when IB equals IBQ. This is roughly equal to delta IC over delta VCE. Okay, so what is that? At IBQ. So that means it should be on this particular graph. It's on this because I have to satisfy this condition. And what you need to get is delta IC over delta VCE. So for a change in VCE, so say from here to here, if it changes this much of around VCEQ, this much of change would produce this much of change in ICQ. So this is my delta VCE and this is my delta IC. So what is that? It's roughly, it's the slope of this curve at this point. Okay, it's about this much. So about this, as this change closer and closer becomes smaller and smaller, it becomes the slope of this curve at this Q point. Okay, so this is the slope of the output characteristic curve at Q point. So HFE is actually the current gain at the Q point, and the HOE, output conductance, 1 over output resistance. It's the slope of the IC versus VCE curve at the Q point. Okay, so those two we know now. If you have the output characteristics, you can obtain two H parameters of your BJT. The second one is the input characteristic. Okay, so this is a functional relationship between input voltage and input current with output voltage as the parameter. Earlier, when we talked about input characteristics, we did not mention anything about the VCE. Now in this case, it's necessary to have a look at it again. So let me draw what we looked at earlier. So the output characteristics, we looked at something like VBE versus IB, and we said it is pretty much something like this. It's a diode characteristic, right? So this is what we said. We did not mention anything about this being a function of the output voltage, and also this is about 0.7, the forward voltage drop. Now let me draw the same figure by interchanging the axis, x-axis and y-axis interchange. So this is now IB, this is my VBE, right? So if I draw the same thing, what I would observe is something like this. One difference that we need to incorporate is what happens when there is a change in VCE. Now this change is very small, but in order to demonstrate what we need to show, I'm gonna mark this a little bit bigger than what it actually is. Okay, so let me use a different color for this. Let's say if I had something like this and something like this for different VCE values, and I'm gonna actually draw the same thing by changing my axis like this, so that I use, for my x-axis I use IB, and for my y-axis I use VBE, so that I just interchange the axis, so that what I have is something like this. Okay, so if you remember what we had for HRE from the previous lecture, was that it is equal to, HR is equal to dabba VBE over dabba VCE at the quiescent point when IB is equal to IBQ. This is approximately equal to delta VBE divided by delta VCE, which we can write as, this has to be on IBQ, IB is equal to IBQ line, so this should be my IBQ, it should be on this line. If VCE changed, accordingly VBE also changed, so that now new points are on each of these curves, red and green curves. So this will be my HRE, delta VBE divided by delta VCE, VBE2 minus VBE1 divided by VE2 minus VCE1. So this is a voltage ratio, and specifically it's a reverse voltage gain. So reverse voltage gain. Similarly, if you remember from the previous lecture, my HIE is equal to dabba VBE over dabba IB at VC is equal to VCE cube. So this is approximately equals to delta VBE divided by delta IB at VCE cube. That's this. So this should be on VCEQ. So it should be on this blue curve. It should be on blue curve, and as IB changes, so let's say it changes from here to here. Actually, we should consider a small change, but let's take that is my delta IB. Then the corresponding change in VBE would be this. This would be my delta VBE. So that ratio. But when IB is made smaller and smaller, this becomes the slope of my curve characteristic at this point. That's my, it's the slope of that. This is my Q point. Okay, so I have HIE is my slope of the input characteristic curve. Okay, so what you see here, the thing to note is that though we assume HIE, HRE, HOE and HFE to be constant values, they actually change. In other words, for example, if we take HOE, right? If I change my IB value or my VCEQ, let's say for example, to make it here, my slope will be drastically different than my slope at this particular Q point. Okay, so therefore, if you change the quiescent condition, it's going to change my parameters. Okay, so the parameters, H parameters are going to depend on these things, but you'll see that these parameters do not change too much within a reasonable range of values. So therefore, if you have, say for example, a characteristic something like this, very much like that, then it will have zero slope. Okay, zero slope means infinite impedance, infinite resistance, zero conductance. Okay, but if they are slanted and parallel to each other, then no matter what the value of your VC, what the value of your IB, they will be the same slope, in other same conductance, right? But you see, a lot of time these slopes change with different IB values. So therefore, actually, the output conductance also changes with that. Likewise, because of the curvature of the graph, different locations will have different curvatures. Like at this point, this much. At here, you have this much. Okay, so at different locations, you have different curvatures. So therefore, HOE value changes, and also because these lines are not parallel, the HFE changes. This is for HOE. Okay, so that's one. And similarly here, you'll have a similar effect for HRE and HIE. So H parameters vary with the Q point because lines are not straight and spaces between them are not even, both in input and output characteristics. This is due to the nonlinear characteristics of the BJT, and also these values can change due to temperature. This can also change due to temperature. Typically, as the temperature increases, a lot of parameters tend to increase, like HFE increases with the temperature. Okay, so let me give you some summary of a typical, what are some typical values of each of these parameters for different transistor configurations, amplifier configurations. So far what we have looked at is only the common emitter parameters, HIE, HRE, HFE and HOE, but this will be similar to other characteristics also, like HIC, HOC, HFC, HRC, and common base parameters similarly be affected. Let me take a sample transistor, a small signal transistor, and list values. Obviously, if you have a different transistor, these values are going to be different, but these are just for your information, some typical values of parameters. Okay, yeah. So for a common limit amplifier, the value is about 1.1 kilo ohms, whereas my reverse gain is about 2.5 times 10 to the minus 4, and this is a gain, so there are no units, so very small value. So that is why, though VCE changes, the effect of it is very small. So if VCE changes by 10 volts, the voltage that is felt in the base side is 2.5 millivolts, right? Very small. That is why it is very small. The effect is negligible. So often we neglect this and approximate it to 0. So it is like 0. Okay. HFE in the range of 50. This is the beta. Okay, this is beta actually. No units. HOE is like 24 microamperes per volt. So this is like 1 over 40 kilo ohms. 1 over 40 kilo ohms, the conductance. Similarly, for common collector, this is similar, 1.1 kilo ohms. Input impedance is similar. So HRC is about 1, not very small like the previous case. So in common collector, we cannot ignore the HRE term. HFC is in the range of, again, like this is the current gain, it's about 51, and HOC again similar to the previous one, about 25 microamperes per volt. So it's like again 1 over 40 kilo ohms. And for the common base, this is about input impedance is much less. It's like 20 ohms, very small. This value is again very small. The HRB like 2.9 times 10 to the minus 4. Again, we can neglect it. And this is very much close. This common base, the current gain is the current buffer. If you remember, in this case, it's like minus 1, so minus 0.98. No units. And output impedance is very high. This is 1 over 2 mega ohms. 2 mega ohms. So it's like 0.49 microamperes per volt. Now, if you remember the amplifier section that we talked about, we had a similar table, except that we did not have this line, right? We had input impedance, the current gain, and we had output impedance. So if you go back and see, you will see that common emitter has about 1 kilo ohms input impedance, just like common collector, and the current gain was about 15 both these, and output impedance was also like this. Whereas the common base, we had a low input impedance of 20 ohms and very high output impedance of 2 mega ohms. So in that particular case, it's a simplification of this H parameter model that we looked at. Okay, all right. So this basically concludes this lecture, and you now understand how to obtain these H parameters using the input and output characteristics. So if you are given only the input and output characteristics, you should be able to at least approximate or estimate the H parameters. Okay, so and then you can uh, do the examples. Okay, thank you.